So these are 6 lecture on module theory. This video on isomorphism in quotient module, some isomorphism theorem or some epimorphism theorem or isomorphic submodule. So this is very important idea to further discussion on module. So we'll just briefly recall what is called homomorphism. To homomorphism from a module to another module, so F is the homomorphism from M to N, is just structure preserving map. What is called structure preserving map? This is just AX is equal to A into Fx. So M and R module on over the same ring, module over the same ring. Otherwise, it's problem because we want to multiply it. Here A is in M and F of X in N. So A should be scalar for M, and similarly A should be the scalar for Fx also. So that's why the over the same ring R, and it should be scalar multiplication should be preserved and the addition should be preserved. So this is the basic idea of any structure preserving map. For a group also, this only the second one is true. For ring, the both one is true, and for field or any vector space, there is only again the scalar multiplication and addition will be true. So which is called a linear transformation for vector space. In module also you can call it is a linear transformation. So it's a structure preserving map. Different type of homomorphism. We know what the different type of homomorphism is. One is called monomorphism. It is injective. It is called monomorphism. If it is by onto, it is called epimorphism. If it is the same, say M or N is same, then it's called endomorphism. So it is called endomorphism. If the both are same, so M or N are same. The endomorphism over M is homomorphism from M to M. So set of all this map, homomorphism map is called home. Home RMN, just this set of all linear map, R linear. R linear means set of all map which satisfies this condition. The set is called home. Home RMN, homomorphism from M to N. This is the collection of functions or linear transformation. It's R linear. So it's called endomorphism. It's the same thing, and if it is a bijection, then it is called isomorphism. If this F is bijective, then it's called isomorphism. And what is kernel? Kernel, you know, the kernel is just set of all X in M such that which maps to the 0 element in N. So for all X such that Fx equal to 0. 0 is in N. So this is the called kernel of this transformation. The kernel F. So if M and N isomorphic, we use this symbol. This symbol means this symbol means it is isomorphic. So M and N isomorphic, that means there is a isomorphism between M and N. So these are some different type of homomorphism. By the way, this homomorphism, this home, this forms a R module over R, because you can just define two functions, like if F and G are in homomorphism, then you can easily define F plus G like that. F plus G, it is just Fx plus Fg. So F and G both in home, so F plus G also in home. Now we have to just define that F of Fa, A into F. So this is by definition this. So you can construct a group module structure, and you can easily check that the conditions of the module is satisfied. The conditions are like this associativity and this other group properties, commutativity, and then the distributive property is is true for this condition. By this definition. So this home is again a ring. So right. So if by the way, the one thing is needed, right? So to be home is as a module, you need this ring to be commutative. Why? Because just so a plus x, a plus g define like that. X goes to fx plus gx, and if af we define like that. So why this commutativity needed? You can easily check that the commutativity is needed. So why this commutativity needed? Because say you want to say why this af is af linear? Yes, af is a function from m to n. Now is af linear? Okay, it is linear. So it's additive. Obviously, it is additive because by definition this is af of x plus af of x. Sorry, af of g. Sorry, af of y. Now, by definition, a f of x is just a f x plus a f y. Now, you take a common, so it is f x plus f y by distributive law of module. Now, this is just f of x plus y. So we have this. So it's additive. But is it scalar multiplication pizza? The question is so whether if I take some cx, whether it is c into a f x or not. So what is this? This is by definition a into f of cx, but this is by definition ac of fx, ac fx. But what is c into a f x? This is just by definition c into a f x. So it is ca f x. So if ac not equal to ca, then these two cannot be equal. So then it is not a linear. So to be a linear, R must be commutative, must be CA equal to AC. So R should be commutative, otherwise your this scalar multiplication will not preserve for AF. AF is additive, but the scalar multiplication not preserved. No problem with F plus G. This is in home. No problem with that. So only problem for AF. AF is additive, but to be AF to be in homomorphism from M to N, that ring must be commutative. So this is the important crucial point, that other than that ring is commutative, this home thing is not modular. So this is easy, and then the important theorem is also called fast isomorphism theorem. Some book is written as fast isomorphism theorem, which is also called epimorphism theorem. So let M and N are epimorphism. From F is from M to N epimorphism. So what is this? So this is onto map. So it is linear and onto. So epimorphism means onto, and also R linear. R linear means you know that f of x plus y is fx plus fy, and f of ax equal to afx. Now let P is the kernel. P is the kernel of that. Then there is a unique homomorphism from, so this f mod m mod p. You know, the in previous video we see what is called the quotient group, quotient module, and from that you can find a map, a bar, which is isomorphic. It will be isomorphism, such that your f equal to, so this is a natural projection map. This is called natural projection map, eta. That eta is goes from M to M mod P, M quotient P. Like what are the element of M mod P? The M mod P elements of the M mod P is all coset like x plus P. Now you just map from x to, it is just like a projection map. It's from x to x plus P. Now this is a natural projection map, and you have a map from M to N F. Now these two are given to us, that f and the eta, and from f and eta we can find f bar, such that this diagram commutes. What is the meaning of this diagram commutes? The diagram commutes means, this diagram commutes means f equal to f eta, f bar compose eta. So first eta, then f bar is actually equals to. So sometimes we call that f is factor through that eta. So is like a factorization. So f is something, some into something. So we can, if we want to take a group structure on that home mn, so we can, there is a ring structure on also this home on home. Then we can say that this there are three elements. F is the one element, and f bar and eta is another element. Then we can say that is not actually not in the home. Actually, that's f tilde is not in the home. Okay, we can't say that because f bar or eta is not in the home. So f is the home of mn. So we can say this is like a factor. You just factorize like a equal to bc, like that. So sometimes we use the composition as a product in ring or in group. So in that sense, it is like factorization. Whatever, this is this f bar. How do you define that f bar? That is the important thing, and why this is isomorphic. That is you need the proof. So basically, the idea behind this is this. So the M is a module, and N is another module, and we have a kernel like P. So every element of P squeezed to a single element here 0. Now there is a natural map. So this is the F map. There's a natural projection map on another. So it is not N, it's M mod P, because and P is now is like a 0 element. So P is like a 0 element, and any element X is mapped to actually X plus P. Now, not only the X, there are several elements also there in the same coset which maps to the X plus P. So how do you define this map? So it is natural way to define that X plus P should goes to that Fx. So where X lands through F. So then it will be commutative. Then eta of X is X plus P, and F till F bar. So F bar eta X is just F bar X plus P, and X plus P maps to the Fx. So it is just you have this. Now question is this well defined? Because this is a question of well defined, because there are several elements which map to the same X plus P, but this X may goes to the different Fx. So the idea is this. So if you have two elements X and Y in M, and your X plus P is same as Y plus P, that means your eta function goes to the same value. Now, is this question is now Fx and Fy may be different. So if this is different, then this F bar is not defined, is not well defined, because F bar, we define F bar of X plus P as Fx, and we define X bar Y plus P as Fy. So if Fx so X plus P and Y plus P is same, so same input, it can't go to the different output. So we have to prove that Fx equal to Fy. Otherwise, this F bar is not defined. So how do you prove that Fx equal to Fy? Now it is easy to check that Fx equal to Fy, because X plus P is equal to Y plus P. That means actually if and only if X minus Y in P, because P is a submodule. The kernel is a submodule of M. So X minus P belongs to that kernel. So this is easy. That's since X plus P is this, so X plus some P1 equal to Y plus some P2. So X minus Y is some P2 minus P1, which is in P. Now this is, since is a kernel, so this is if and only if f of X plus Y, X minus Y is 0. So it is in the kernel. P is the kernel. Now since P is a kernel, so and f of X minus Y is 0, but by linearity this is nothing but f of X minus f of Y is 0. So by linearity it's Fx equal to Fy. And where's so and not only for this kernel, if you actually kill all this element of the kernel, then all the not all the element of the kernel. Yes, if you kill all the element of the kernel, so you just take all the element of the kernel like a 0. And not only that, if you take a bigger, if you take a submodule which is P is as a submodule, if you take a bigger superset, so say another, say Q is a submodule of M, and P contained in Q, then also we can define this that F bar. the same thing will happen, because we have to just prove fx equal to fy, and fx equal to fy, because that you kill this, it is not just m mod p, if you just kill this or every element other than that also. So the bigger set go to the 0 element. So then fx equal to fy, but then it will be not the isomorphism. It will be injective but not the isomorphism. So why this is isomorphic? Then you have to, so it is well defined, you have to prove that is isomorphic. Isomorphism. So why this is isomorphism? So to show this isomorphism, you have to show injective and onto both. So why this is injective? So if x plus p is not equal to, you have to show that if there are two different elements, then go to the two different elements. If f bar x plus p should be, so you have to show that x bar, to show that f of x bar this not equal to this. That is the definition of injectivity. So two different elements are input, the output must be different. Why this is so? So this is clear that f bar x is actually fx and fy, this is fy. But why this fx and fy is different? This is just, so it's equivalent to show that fx and fy is different. Why fx and fy is different? Now this, since x plus y p is not equal to y plus p, that means x minus p not belongs to that p. And since x plus y, so x plus y not belongs to the kernel, that means x f of, that is equivalent to say that f of x minus y not equal to 0. So since it's not in the kernel, so that's why this is injective, and you have to show that it's onto. Why this onto? So to show onto, you have to take a pre-image of every element of n. So take an element on y here. Now we are going to use that epimorphism thing. We still, till we do not use that epimorphism thing. Oh, the f is onto, that we have not used here. Now we are going to use that f is onto. Since f is onto, we have an element x here, such that fx equal to y. Oh, there exists an x in M. For every y there is an x in M, such that fx equal to y. And now we are going to show that f bar x plus p is just y, and that is because it is just fx and fx equal to y. So using that epimorphism, this function is f is onto, that's why the f bar is onto. So this is onto, injective, well defined, everything is there, so it is isomorphism. By the way, you have to just one more thing, you have to show it is a linear, that also you have to show, and you can easily check that this is linear. So this is linear. You have to show one more thing, that f of x, and you can easily check that because, sorry, it is x plus p. So it is, if you take a two element here, so we first the linear sum. So if you take x plus p and another element y plus p, now this x and y both in now M, then you have to show that this is just f of x plus x, f bar x plus p plus f bar y plus p. That you can easily check that, because x plus p plus y plus p is just x plus y plus p, and x plus y plus p is just f of x plus y, and right hand side also f of x plus f of y. Similarly, you can check the x bar, f bar of a x plus p is just a into fx, and that can be easily shown because a into x xp is just ax plus p. Again, because p is submodule, that is ap is ap, that everything is needed here. Why m is submodule and this epimorphism thing. So this is the first isomorphism theorem. It says that if you quotient by the kernel, then it is actually isomorphic to the range set. Now there is a idea is this. So if you have a map m from n, and if you this map kill all this element in this kernel, that means basically you just think that as a 0 element. That's why we are going to the m mod p. So you can think that as a m mod p. Now what are the other submodule in m mod p? So if there any submodule in m which is bigger than p, so if there is a think let's say n is there, so bigger submodule. So n is between P and M. And what happened with this n in this quotient quotient module? We see in the previous video that is actually submodule of n mod P. So M mod P, sorry, is the other way. Sorry. Because the elements of n, which in P also, that goes to 0, and elements of n which is not in P, that not to go to the 0, and that forms a submodule in the quotient structure. So n mod P is a submodule of M mod P, and P mod P is just a single, this is a 0 element actually. Now we can talk about this thing. So if you now, since n mod P is a submodule of M mod P, so we can talk about the quotient. We can talk about the quotient. So M mod P quotient by n mod P. You can always quotient a module with another module. So it is a quotient of quotients. So it's a set of sets like that. Set of sets is a set of sets, and this module actually set of sets like that. So hierarchy is a 2-3 tier. Now this can, there is isomorphic. This is isomorphic to actually M mod. The idea is this: you first kill this element of P. You just first identify the element of P like 0. In the next step, you are going to identify the all element n mod P that is actually here. This are going to kill in the next step basically. So there are two quotient of quotient, and that means you can just do it in the single step. Just kill all this element of n. But remember, these two as a set, they are not equal, because the right hand side is a set of set and the left hand side is a set of set. The quotients are the set in M mod n. So M mod n module is a set of set. M is a set of element, and element of M mod n is quotient, which is set. No, the module M mod n is set of set. It is a collection of sets, some quotients, and M mod P quotient by M mod n mod P. The elements are set of set. This, so the left hand module is set of set. So remember, the left hand side is a set of set, and the right hand side is set of set. So this can't, as I said, they can't be equal, but there is isomorphism. In the natural isomorphism, you can easily, there is a natural isomorphism. You can easily check what is the, you can easily find that what will be the natural isomorphism. And this actually, this diagram will you commit that what are the diagram? The diagram is M is here, and your M mod P quotient P is here, and here M mod. So this is a subset. M mod P is a subset. This you have a map. Say it is eta P. Say eta is a natural projection map on P. So x plus P goes to fx like that. So x plus the P goes to 0 basically. X plus P goes to x goes to x plus P. Sorry, x plus P. No. So x goes to x plus P. So here, if you take x, here M mod P, there is x plus P. X goes to x plus P. And similarly, here is a natural projection map eta n, which is x goes to x plus n. Now there is a map. That map is called eta. This is also a projection map, natural projection map. Now what is this eta Pn? Eta Pn is from M mod P to M mod n. Now element of M mod P is just x plus P, and here is just x plus n, and this maps to this. So this is the map. So eta. So you have to define. You have to show that it's well defined, and you can easily check it is well defined because P is subset of n. So everything kill in P is should kill in n. Everything 0 in P is, if x belongs to P, then x belongs to n. So that is well defined. Now we have to define a map from M mod P mod N mod P. So we are going to now another module, it's a more higher order. So this, because in N mod P is a submodule of N mod P. So you have again there is a projection map, because it is a like a projection. You have a natural projection map. That map called eta N mod P. So you are killing all this element of N mod P here. Now you have to define this such that the whole diagram is commit. So everywhere is commit. That means eta N equal to eta P compose. Eta P N compose eta P. And again, this map say called eta bar. Eta bar. So eta Pn is just eta bar compose eta np. So how do you define that? And that is just you just forget about the upper part. So you are going to in the lower part and use the first isomorphism theorem here in the lower part. You forget about the m. There is a m mod p is one module and m mod n is another module. So you think about like m. This is like m. This is like n. And you are going to kill this n mod p. So if you show that this is the kernel of this map, if the kernel is this, if the kernel of eta pn, if you can show that the kernel is actually n mod p, then it is done. This is by first isomorphism theorem. This whole diagram is commit. Both diagram is commit, because the lower part is that's the first isomorphism theorem. Just flip it in this. So this is the idea. So that m n and this m mod the kernel. So here m in the replaced by m mod p and n replaced by m mod n, and you have to show that the kernel of this map is just n mod p. Then you can show this. You can say that this is a isomorphic this eta n, and eta n just nothing but this. How do you define that? So this is the f bar of f. So you are going to define f bar of f via that natural quotient map. You have to again define that eta bar as a just eta np, that you have to lift that eta np to say that eta np bar. So you just define that like that, and just you have to show that the kernel is this. Then proof is just from the first isomorphism, and it's easy to show that kernel of this is np. So that is easy. So if you take the kernel, so this is, you have to show that is a kernel. So you have to show that this eta pn, that map of any element here. So any element is like x plus p. It just defined like x plus n, and you have to show the kernel of this. So is this the kernel of this is just n mod p. So all the elements are x is just n mod p, that is n plus p. So because every element, it is actually, it's a 0. Sorry, 0. So you have to show that that x is actually belongs to n, and that is easy because in right hand side that every element of n is 0, and n contain p. So now if x in n, then it is 0. If x is not in n, then it is not 0. So kernel is actually the all element of x. Set of all x such that this goes to 0. The kernel is actually n. You can't say it is n, it is n mod p because you in the quotient ring. So using the first isomorphism theorem, you can easily show that the lower part, using the lower part, the first isomorphism theorem on the lower part, you will show that that quotient of a quotient is just a quotient, isomorphic quotient. So it's just idea is this: you are just killing the element in the 2-step, and you can just kill in the single step the whole set of n, the element of n. What is the quotient of a sum now? If m and n is a 2 submodule, but may not be p is in n, may not be n is a subset of n, may not be n is a submodule of p, may not be the p is a submodule of n. Then what happens? Then we have to go into the more bigger module, p mod n, which is p is a submodule and as well as n is a submodule. Now we can use this isomorphism theorem on that quotient. And if you just see that if you use this isomorphism quotient, then p plus n mod p plus n, and you are killing the element of n, p, in p plus n. Now once you killing the going to 0 the all element of p, some element of n also going to 0. But what are the elements where the elements of n who are going to 0? Just precisely the element of n intersection p, where the elements are in p and n both, that element of n is going to be 0. That's why it's same as if you have quotient that n by n intersection p, the element of n intersection p in n, you are going to kill that element. Is actually p plus n mod p, so they are isomorphic. But this is a basic idea. That similarly, p plus n mod n is just p mod n intersection p. So, but you have to need a rigorous proof of that. So, and by the way, that the previous two theorem, that first isomorphism theorem, that is also called second isomorphism theorem in ring theory. And ring theory, you will see that that there are similar theorem in ring also. There's ideal, then a sub-ideal, then and quotient by that, this thing. A similar idea of the ring also. But this has no parallel theorem in ring. So there are two first and second isomorphism theorem, and this is we can say the third isomorphism theorem. But in ring theory, you have no this type of theory. First and second is there, but no parallel idea of that. So how do you define that function? So how do you define that function from Pn to, you have to define some function from here to here. So basically you have to define a function from P plus n to n mod n intersection P. And once you so function is a G, and if you can show that the kernel of this function is P, just done. If you can, oh, by the way, you have to show this is surjective. There you have to, again, sorry. You have to show this function is surjective, that eta Pn is surjective. Otherwise, it's not isomorphic. That you can easily show. And so you have to show that this function is surjective. You have to define a function such that the function is surjective and the kernel is n, and then first kernel is p. Then first by first isomorphism theorem, you can show that you can say that p plus n quotient p is isomorphic to the range set. So what is the definition? How do you define that? Nothing natural choices. So what are the element of p plus n? The element of p plus n just x plus y, where x is from p and y is from n. Now, what will be the natural choice for that gx plus y? You are taking the all elements of n mod p, n intersection p going to be kill 0. So the choice is like that. You should define that that y, because you are all the element of y you are just try to keep there, but all the element of p are going to 0. So you just take y as that. Don't put x, because in that case x will not kill. You want to kill x, so you are putting y, and this is a quotient, so it is a quotient. So it is actually set y plus n intersection p. Now this is a definite. You define that. Now we have to show this is well defined. How do you show this is well defined? Because to show well defined, you have to show what you have to show. If you x1 plus y1 is x2 plus y2, then you have to show y1 plus this. So it's to show actually. So well defined, you have to show that y1 plus n intersection p is equal to y2 plus n intersection p, and that is trivial. That is trivial. That is trivial because from here you can easily find that x1 minus x2 is equal to x2 minus y2 minus y1, and since y2 minus y1 is p and x2 minus x1 is, sorry, x2 minus x1 in p and y2 minus y1 in n, and that means that if the two are elements same, that means they belongs to the in this intersection. So since there belongs to the intersection, y2 minus y1 in the intersection, that means y1 plus that set y1 plus this submodule is same as y2 plus that submodule, because they are in intersection. The difference in intersection, like the same thing as like a group. If difference x y inverse in that group subgroup, then x quotient of x is same as quotient of y. You are just see in the group theory in the quotient group like that by some normal subgroup. So this is well defined. Now we have to show that this is onto, and the kernel is this. So you have to show two more things, that this kernel is this. So how do you show that kernel is this? So x plus y you are going to taking as a 0 element R. So 0 element is nothing but n mod p, n intersection p. Now by definition, what is this? By definition, it is by definition, what is this? So this is this. By definition, the x plus y is this, and if they are is same as that 0 element, that means your y in this. So once y in this, that means y is in P, and since y is in P, that what you show? So kernel is P. Yes, the kernel is P. So once we have this, now x in P, so x plus y, so x plus y in P. So we already x in P, and we have showed then that y is in P, so x plus y in P. So that means every element which goes to 0, that means in P. But you have to show the other way also. The other than that elements is not in the kernel, then if you take the outside from this set P, it can't be good to the kernel. So that is actually if and only if. So this is if and only. So that's why it's kernel. So this is if and only if. So kernel is P. So every element of P goes to 0. No other element of other than outside P is going to 0. And last thing you have to show that is the epimorphism. You have to show this is onto map, and that you can easily check. To take an element y plus n mod P, n intersection P, and how do you take the x? How do you get rid of the x? If you have the right hand side, how do you get rid of the x? Because the element of how do you get rid of x? So you have to show that there is an exist x in P such that you have to find this x such that this will happen. So now there is no such x is given to you, y is given to you. Now since n intersection P, since the right hand side you have there is an element in intersection P, you can take that. Okay, no, you just take g of g, that is also this. Oh, no need of taking. So you can take x as 0. Take x as 0. Because by definition, g of x plus y is just y plus n intersection P. So g of 0 plus is y is also this. So it just x takes as a 0. So x is taken. So onto. So for every y we have a x. So that x is 0. You have another choice of x also, but we just take x as 0. So this is the third isomorphism theorem, like sum of the quotient, and this is very important. That sum of the submodule. So sum of the submodule is also important thing. So what is n plus k? If n and k are two submodule, it is just nothing but the n plus k such that n in n and k is k. So this is capital K, this is small k, like that. And you can easily show that this set can be made as a R module. So this is called submodule S generated by this n and k, and this is the smallest submodule containing this. So easily you can easily show that first of all, this n is a subset of this. Take the k as 0, and k is a subset, n as 0. Now these two are submodule number 1, and this is the smallest submodule containing these two. You can have no more submodule which is less than strict subset of proper subset of n plus k, and still n and k is a submodule. You can't do this, because once you take the all element of n and once you take the all element k, then you have to take the element of n plus k, because since this is a module, you have to take the element of n plus k, element n plus k for all n and all k. So that is the smallest submodule. Now we can extend that idea to the larger class. So if some n1 n2 n dot n1 n2 dot, so nr are different finitely many submodule, then you can easily define how what is the smallest submodule containing all these submodule, and this you can write as a sum n1 plus n2 plus dot 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 nr, and each ni is from ni, n1 from n1, and this for all I. So this is the idea. You can extend this idea to the finitely many submodule, and this again a submodule which is smallest submodule containing n1, n2, nr, and sometimes it's called write as a like intersection of all submodule which contain n1, n2, nr. And that's all for this video.